Okay, students, in the today's class or video, we will start discussion on Unit 4. Okay, so in the Unit 3, we have discussed the momentum principle. Based on the momentum principle, we have derived the Euler's motion equation considering two external forces, that is the volumetric force and the surface forces which are acting on the surfaces of the plane. Okay, and just by integrating the Euler's motion equation, we have also derived the Bernoulli's energy equation, and we have made certain assumptions while deriving the Euler's motion equation and also the Bernoulli's energy equation. So those things we have already discussed in the earlier videos and also classes. So you please go through those videos. Okay, how we have derived the Euler's motion equation and what are the assumptions we have made while deriving the Euler's motion equation. And Euler's motion equation we have derived for the ideal fluid. Afterwards, after applying the certain corrections, we have applied it to the real fluids. Similarly, Bernoulli's energy equation. So while deriving the Bernoulli's energy equation, we have integrated the Euler's motion equation with some assumptions. And the Bernoulli's energy equation, it gives the energy head, not the energy possessed by the flowing fluid, but it gives the energy head possessed by the flowing fluid. That's why its dimension is in meter, E. Even though we are calling it as the energy equation, but whatever E value we are getting, it is the energy head. And we have also discussed the applications of Bernoulli's energy equation. So the main applications, so Bernoulli's equations, energy equation, we are applying to analyze any type of incompressible fluid flow problems. Whenever it is required to analyze and get the solution for the incompressible fluid flow, that is the water, then we are using the Bernoulli's energy principle. So some of the applications we have discussed in the earlier videos, that is the free vortex, forced vortex, then the measurement of rate of flow through the closed conduits. So the measurement of rate of flow through the closed conduits, we have used two mechanical devices, that is the Venturimeter and Orifice meter, and we have derived the equations. So all these things we have discussed in the earlier videos. So in the Unit 4, again we will discuss the application of Bernoulli's energy equation to measure the rate of flow through the tanks or through the open channels or canals or the natural streams. Okay, that is, if it is required to know what is the discharge in the man-made canal or in a small channel or in a tank. Okay, so how to measure the rate of flow or the discharge? So we are using some mechanical devices. So we will discuss those things in the Unit 4. In the Unit 4, mainly we are discussing the orifice and mouthpiece, orifices and mouthpieces, or orifice and mouthpiece. Then the second type of devices, notches and weirs. Notches and weirs. Okay, so these things we will discuss in the today's class, that is the orifice and mouthpiece. orifice and mouthpiece are the measuring devices which are to be used to measure the rate of flow through the tanks or through even closed conduits also. Okay, through the tanks. Then the notches and weirs. Notches and weirs are also the measuring devices, and they are using to measure the rate of flow through the canals or through the channels or through the natural streams. Okay, so first we will discuss the orifice and mouthpiece. What is orifice? Okay, next is what is the orifice? Okay, so first we will define what is orifice and what is the mouthpiece. Orifice is a opening. Okay, orifice is a small opening of any cross section. Is a small opening of any cross section. The cross section may be circular, rectangular, or triangular, and it is fitted at the side of the tank or at the bottom of the tank. Suppose if you have a tank like this, okay, this is a tank, it is filled with the water. So sometimes we know what is the time required to empty this tank or the rate of flow through this tank. So for that we are using the orifice. Okay, as I have told, orifice is defined as it is a opening of any cross section which is fitted at the side of the tank. Okay, this is the side of the tank, so here it is fitted. The shape of this may be circular, or it may be a rectangle, or it may be of triangular in shape, or V notch. Okay, it is a triangular in shape. So either it is fitted at the side of the tank to know so when the orifice is fitted at the side of the tank, then this fluid, it tries to come out through this opening. So this is the fluid which is coming out from this fluid. So with the help of this you can measure the rate of flow. It is nothing but discharge Q. Or this opening may be fitted at the bottom of the tank. Okay, so this is the simple definition of the orifice. Orifice is a small opening of any cross section fitted at the side of the tank or at the bottom of the tank to measure the rate of flow through the tank, to measure the rate of flow and the shape of orifice. It may be a circular, or it may be a rectangular, or it may be a triangular. Okay, next is what? That is the mouthpiece. Second is the mouthpiece. So what is mouthpiece? Mouthpiece is a small pipe. Okay, fitted at the side of the tank or at the bottom of the tank to measure the rate of flow. To measure the rate of flow. Mouthpiece is nothing but a pipe which is fitted at the side of the tank like this. Okay, suppose this is the tank. Okay, if it is required to measure the rate of flow, so you can fit a mouthpiece at the side of the tank or at the bottom like this. Then this is a pipe. So then what is this length? How much length we are supposed to take? So this length of mouthpiece, normally it is 2 to 3 times. 2 to 3 times the diameter of pipe. The diameter of pipe. Okay, if the diameter of this pipe is D, then the length of orifice, the length of mouthpiece L is equal to 2D or 3D. 2 times the diameter of pipe or 3 times the diameter of mouthpiece. Okay, so what is the definition of mouthpiece now? Mouthpiece is a small pipe. Normally its length is 2 times the diameter of pipe or 3 times the diameter of pipe, and it is fitted at the side of the tank or at the bottom of the tank to measure the rate of flow, that is Q, to measure the Q. Okay, so these are the devices, that is the orifice and mouthpiece. Okay, so we have discussed the definition of orifice and the definition of mouthpiece. The definition of orifice is what? The orifice is defined as, it is a measuring device which can be used to measure the rate of flow through the tank, and it is a small opening of any cross section. Orifice is a small opening of any cross section. Normally the shape of the cross section, it may be circular, rectangular or triangular, and this small opening is fitted at the side of the tank or at the bottom of the tank. Okay, then mouthpiece, it is defined as, it is also a device, mechanical device, which is used to measure the rate of flow through the tank. It consists a pipe, and normally the length of this pipe is 2 times the diameter of pipe or 3 times the diameter of pipe, and this is fitted at the side of the tank or at the bottom of the tank. Next is classification. Classification of orifices and mouthpieces. See, students, already we have uploaded all these notes in the PDF form in the extra day only. So you please go through those notes. In those notes or in the notes, we have clearly explained the definition of orifice and definition of the mouthpiece. So this is the video. This video also we are going to upload. Please you go through this video and also the uploaded PDF notes. Okay, so now the classification of orifices and mouthpieces, it is also given in the notes also. So the orifices may be classified as the small orifices and large orifices. Small orifices or large orifices. It depends upon the size of the orifice and head of the fluid above the orifice. Okay, first classification is the orifice. It may be a small orifice, it may be called as a large orifice. It depends upon the size of the orifice and the head of the fluid above the orifice. Okay, that is, what is the head of the fluid? This is the head of the fluid. This is your orifice and this is the head above the orifice. So to classify small orifice or large orifice, it depends upon the size of the orifice. It may be small or it may be large, and also it depends upon the head over the orifice. Okay, then what is large orifice? Large orifice based on head, H above orifice, Okay, if the head of fluid H above the orifice is 5 times, okay, if this head H, okay, if it is more than 5 times the diameter of orifice, that orifice is called large orifice. Okay, large orifice means H is equal to 5 times the diameter of orifice, or it is more than 5D, more than or equal to 5D. Okay, then you say this orifice is a large orifice. Okay, large orifice, when you can say it is a large orifice or it is a small orifice, depending upon the head above the orifice. If the head above the orifice is 5 times the diameter of the orifice, if it is a circular orifice, okay, or if it is a rectangular, 5 times its height of the orifice, that type of orifice is going to call as the large orifice. And if this head is less than 5D, then you can say it is the small orifice. Oh, sorry. Okay, it is the small orifice, and large orifice H is less than or equal to 5D. Okay, so the orifice may be classified as small orifice or large orifice. It depends upon the size of the orifice. If the head over the orifice is more than the 5 times the size of the orifice or diameter of the orifice, that orifice is called small orifice, otherwise it is called large orifice. Okay. Then next is, you have sharp edged orifice, and bell-mouthed orifice. Then also third type, free discharge and free discharge and drained or submerged orifices. Okay, these are the classifications. The orifices and mouthpieces may be small orifice or mouthpiece, large orifice or large mouthpiece, and you have also sharp pressure orifice, bell-mouthed orifice, and if it is a free discharge based classification based on free discharge mouthpiece, drained type of mouthpiece, submerged type of mouthpiece. Now we will discuss in detail and we will derive the equation for the mouthpiece and for the orifice applying the Bernoulli's energy equation. Okay. Let us take flow through orifice. We will discuss first the case flow through orifice. First case, flow through the orifice. Okay, suppose you take this sketch, this is the tank, this is the tank, this is filled with the water and this is the jet of fluid which comes out from the, and how the fluid enters this. Okay. If a small orifice is pitted at the side, this is orifice is nothing but a mouth, it is a opening. So the fluid will enter and it starts flowing in this. Let us consider a section here. Let this section is 1, 1. Let this section is 1, 1. This is the jet of water. Jet of water. Coming out from mouthpiece. Coming out from the mouthpiece. And let us take another point very near to the opening. So you take this section or this is section small a. Now this is the center line of the mouthpiece. This is the mouthpiece, may be circular or it may be rectangular. Now you consider one point at section A, another point at section 1, 1. This is called vena contracta point. Vena contracta point means the jet will flow horizontally up to this point, then it bends. Okay, then the fluid will starts flowing in the vertical direction. So this is point 1 you can take, this is point 2, this is point 2. Okay. Now, okay, so let us now we will apply the Bernoulli's energy equation for this. So what we have considered here? We have considered a tank. This is a tank filled with the water, which is incompressible fluid, and a orifice is pitted at the side of the tank. At the side of the tank. Now, when the orifice is going to fit at the side of the tank, then the fluid inside the tank or the water inside the tank, it starts or it will try to come out through this orifice. Okay, so this is the jet of water. So let us take two sections, AA and 1-1. Section 1-1 is taken at the vena contracta point. Section AA is taken just upstream side of the mouthpiece, just extreme side of the orifice. Sorry, it is a orifice, just upstream side of the orifice and just near to the boundary of the tank. Now you apply the Bernoulli's equation. Let this is H, this is the head over the, this is the head over the orifice. Okay, now applying the Bernoulli's equation, okay, at point 1 or at section 1-1, that is, one is the pressure head. Let P1 is the pressure intensity at point 1, okay, plus let velocity at section 1-1 is V1 square by 2g plus Z1. This is equal to, now applying the Bernoulli's energy equation at section 1-1 or at point 2, let pressure intensity at point 2 is P2 by W plus V2 square by 2g plus Z2, where P1 pressure intensity at point AA, or at point 1 or at point 1 or at section AA. Then similarly V1 is the velocity of fluid at point 1, P2 again it is the pressure intensity at point 2 or at vena contracta at point 2, or it is taken at the section 2-2. Then V2 is the velocity of flow at section 2. Now taking the center line of the orifice itself as the datum, then you have Z1 is equal to Z2. Then the equation becomes P1 by W plus V1 square by 2g. This is equal to P2 by W plus V2 square by 2g. Okay. Now, what is the P1 by W? P1 by W is nothing but the pressure head. So, what is the pressure head at section 1-1? It is capital H. Okay. The pressure head at point 1 is P1 by W, or it is H. Now, let us see what is the pressure head at point 2. See here, the pressure head at point 2, the fluid is now, it is coming out through the orifice from this tank. So here it is the pressure is atmospheric. So this point is in the atmosphere. So the pressure head, that is P2 by W at point 2 is 0. P2 by W is equal to 0 because pressure is atmospheric. Okay, at point 2 it is exposed to the atmosphere. So at this pressure head is atmosphere. So you can take P2 by W is equal to 0. Now substitute these values, that is P1 by W is equal to H plus V1 square by 2G. This is equal to P2 by W is 0 again, plus V2 square by 2G, or H is equal to V2 square by 2G minus V1 square by 2G. Okay. As now let us take this is as equation 1. This is take equation as 1. Now you observe the equation 1, that is the pressure head H is equal to V2 square by 2G minus V1 square by 2G. Okay, so what is velocity at point 1? V1 is the velocity at point 1. So before going to fix this orifice, this is the static mass of fluid. This is the static mass of fluid. When the orifice is going to fit at the side of the tank, then the fluid starts flowing. So the velocity at point 1 is very, very small as compared with the velocity at the point 2. Hence, it can be neglected. Okay, the velocity, okay, next you can take velocity V1 is very, very small, as compared with velocity V2 at point 2. Okay, velocity V1 is at point 1, which is very, very small. Then velocity at point 2 is V2. Okay, so V1 is very, very small as compared with V2. So the V1 is to be neglected. When it is neglected, H is equal to V2 square by 2G, or V2 square is equal to square root V2 square is equal to 2GH, or V2 is equal to square root of 2GH. This velocity of orifice is going to call theoretical velocity. Okay, so you have to find the theoretical velocity of the orifice. It is not the actual velocity, because there is the loss of velocity due to orifice. Okay, it is not the actual velocity, but you are getting the theoretical velocity. Theoretical velocity is equal to V2, or theoretical velocity through the orifice is equal to square root of 2GH. What is the G? It is acceleration due to gravity. What is H? It is head of the fluid in the tank over the orifice. Okay. Then based on this theoretical velocity, we have three types of efficiencies. That is, they are called hydraulic efficiencies. Hydraulic efficiencies. Okay, this is the theoretical velocity, but actual velocity is something. So you have to apply some corrections to get the actual velocity. So there we are using certain coefficients. So those coefficients are called hydraulic coefficients, or hydraulic coefficients. Okay, one is CV, and one is a CV, that is coefficient of velocity. that is CV. Another is CC, that is coefficient of contraction. Coefficient of contraction. Then another is CD, that is coefficient of discharge. Coefficient of discharge. Okay. To modify the derived equations, so this is a derived equation for the theoretical fluid. Okay, that's why we used to call it is the theoretical velocity. Okay. But actually in practice the fluid is not the ideal, but it is the real fluid, and also whatever velocity we are getting through the orifice, okay, there is loss in velocity because of the orifice. Okay, so now to get the actual velocity, actual discharge through the orifice, we are making some hydraulic coefficients. Those hydraulic coefficients are coefficient of velocity, coefficient of contraction, then the coefficient of discharge. So then what is CV? CV is that what? Coefficient of velocity, and it is defined as theoretical velocity divided by actual velocity. So coefficient of velocity CV is defined as, it is the ratio of theoretical velocity by actual velocity. Okay, so okay, now I will remove this. CV is equal to it is the V theoretical divided by V actual. V actual divided by V theoretical. V actual divided by V theoretical. Okay, so the coefficient of velocity CV is defined as actual velocity of the jet which is coming out from the orifice divided by the theoretical velocity of fluid which is coming out from the orifice. Okay, the velocity of coefficient CV is defined as, it is the ratio of actual velocity of jet which is coming out from the tank through orifice divided by theoretical velocity of fluid which is coming out from the tank through the orifice, or V actual velocity which is coming out through the orifice is CV V theoretical, or CV square root of 2GH. That is, this is the, we already derived, this is the theoretical velocity. So actual velocity is coefficient of velocity, it is a CV, it is a constant, or you can call it as the coefficient. So it is constant or coefficient of velocity multiplied by the theoretical velocity. Theoretical velocity is 2GH. Similarly, next is what? Coefficient of contraction. Coefficient of contraction CC. Okay, next is coefficient of contraction CC. It is defined as, the cross-sectional area of the vena contracta divided by the cross-sectional area of the orifice. Okay, CC, that is the coefficient of contraction, or a constant CC. It is defined as, it is the ratio of area of vena contracta divided by area of the orifice, actual area of the orifice. That is AE divided by A. AA or we can write C. AC divided by A. AC is what? Area of vena contracta. Then A is the area of orifice. Okay, this ratio is called coefficient of contraction. The next is CD. So we have defined CD in the last class only. CD is what? It is the coefficient of actual discharge divided by the theoretical discharge, or coefficient of discharge CD is equal to actual discharge Q actual divided by Q theoretical. Okay, Q theoretical. So these are the three hydraulic coefficients or the constants what we are using to measure the rate of flow through the orifice or through the mouthpiece. Dear students, in the 5th semester, when you are going to visit the fluid mechanics lab, you are supposed to conduct some of the experiments on orifice, on mouthpiece, on the notches of different shapes, and also weirs of different shapes, and also venturimeter and orifice meter. So whenever you will come to lab during the 5th semester, we will repeat these things once again. So in this semester, you are supposed to study only theoretical part of this orifice and mouthpiece, notches and weirs, venturimeter and orifice meter. But when you are going to visit the laboratory, there you will see all these measuring devices which are available in our fluid mechanics lab, and there is also some exercises to conduct the experiments and find out the coefficient of discharge, head over the sill of the notch, okay, etc. So those experiments you can conduct. Please you go through this. In the next class, we will solve some numerical problems on this, and we will go to free orifice, partially submerged orifice and fully submerged orifice. Okay, thank you.